Welcome back to the deep dive. I want you to try something for me right now. Just listen to the sound of my voice. Really listen to it. I am essentially just pushing air out of my lungs, vibrating some vocal cords, and flapping my tongue and lips around to make noise. I mean, it's a purely physical, biological act.
It is a bit messy when you describe it like that.
It is, but here's the magic trick. You aren't hearing noise. You aren't hearing tongue flapping. You're hearing ideas. You're hearing meaning. Somehow, this physical meat noise is translating into abstract thoughts inside your mind. And that transition from the physical brain to the abstract mind is arguably the biggest puzzle in the universe.
And maybe the most contentious one.
Right. Today we're unpacking a fascinating work titled Language, the Mind, and the Brain, a historical synthesis by Alan Garnham. And honestly, synthesis is a polite word for what actually happened. This is really a story about a massive, centuries-long divorce between the people who study the mind and the people who study the brain.
It's like a detective story where you have two detectives working on the same crime, but they refuse to speak the same language. They hate each other's methods, and they work in completely different buildings.
And we're going to find out if they ever actually solve the case. So let's start at the scene of the crime. Why did we separate the mind and the brain in the first place? To me, sitting here in the 21st century, it seems obvious that my brain is my mind. If I damage my brain, I damage my mind. Why wasn't that always obvious?
Well, it feels obvious to you because you live in a world that's just, defined by neuroscience and biology. But if you rewind the clock to the roots of Western philosophy, you run into a very sticky concept called substance dualism. And this really starts with Plato.
Okay, lay it out for me. What's Plato's beef with biology?
Plato was obsessed with the idea of perfection. He believed in what he called forms, these perfect, timeless concepts. Think of a circle. You can draw a circle in the sand, but it's going to wash away eventually. It's imperfect, it's material. But the idea of a circle, the mathematical truth of it,
That's timeless.
it's timeless. It never decays.
So he thought the human intellect was like that perfect circle.
Precisely. He argued that because our minds can grasp these timeless, eternal truths, the mind itself cannot be made of physical stuff. Physical stuff rots. Ideas don't. Therefore, the mind must be immaterial.
So the hardware, the brain, is just meat that rots, but the software, the soul or the mind, is something divine and separate.
That is the seed of the split. Aristotle, he kind of muddied the waters a bit. He thought the soul and body were linked. But then René Descartes came along in the 17th century and basically built a brick wall between them. He's the one who really formalized the split, the mental world and the material world.
And I'm guessing this philosophical wall caused some problems when people actually started trying to study how we think.
It caused a disaster. It essentially split the research community into two different species. On one side, you had the mind people, psychologists, linguists, philosophers. They studied the rules, the grammar, the abstract symbols. They didn't care about neurons, they cared about the system.
And on the other side,
The brain people. Neurologists, biologists, anatomists, they were the ones cutting things open. They were looking at blood and tissue. And the problem was they developed completely different vocabularies.
they weren't speaking the same language.
Not at all. So if a linguist talked about a noun phrase, the neurologist had no idea where that lived in the skull. And if the neurologist talked about the temporal lobe, the linguist didn't see how that helped explain why we use the past tense.
A complete communication breakdown in the study of communication.
And it stayed that way for a long time. Even though we've sort of moved toward physicalism in the last century, the idea that everything is eventually physical, the research traditions really stayed in their separate corners.
So let's look at that first corner, the mind, the software guys. The source mentions that humans have been analyzing language for thousands of years. I mean, Sanskrit scholars were doing it 3,000 years ago. But studying the psychology of it is new.
Relatively new, yeah. The real kickoff was in the late 19th century with a guy named Wilhelm Wundt in Germany. He's often called the Lost Pioneer. He set up the first psych lab, and he was asking all the right questions about how the mind processes sentences.
But I've barely heard of him. Why is he lost?
Bad marketing, mostly. His work just wasn't translated well into English. But more importantly, the United States was getting swept up in a completely different movement, a movement that wanted to throw the mind out the window entirely. Behaviorism.
Ah, yes, B.F. Skinner, the pigeon guy.
The pigeon guy. Behaviorism was a reaction against all that, fuzzy talk about thoughts and feelings. Skinner argued that you can't see a mind. You can't measure a thought, so why study it? All you can observe is the input, the stimulus, and the output, the response.
So in Skinner's view, language isn't special, it's just a trick we learn.
Exactly. He published Verbal Behavior in 1957. And his theory was simple. A child says cookie. The parent gives them a cookie. The child thinks, aha, that noise gets me a snack. They're conditioned to speak, just like a rat is conditioned to press a lever.
It sounds logical on the surface, but the source says this theory got absolutely demolished a few years later.
Demolished is the right word. In 1959, Noam Chomsky wrote a review of Skinner's book that is, well, legendary in academic circles. It was scathing. Chomsky pointed out this massive, gaping hole in the behaviorist argument. He called it the poverty of the stimulus.
Poverty of the stimulus. That sounds like a heavy metal album, but what does it actually mean for, say, a toddler?
Okay, think about the data a toddler actually gets. Your parent. Do you speak in perfect, grammatically complex textbook sentences to your 2-year-old?
God, no. It's mostly, no, don't eat that, where's your shoe? Or just rambling nonsense while I'm trying to find my keys. I stutter, I restart sentences, I mumble.
Exactly. The input, the stimulus is poor, it's messy, it's broken, it's full of errors. And crucially, you don't teach them grammar. You don't sit a 2-year-old down with a whiteboard and explain the difference between a subject and a predicate.
I definitely don't. If my kid says, I want juice, I don't say good use of the objective case. I just get them the juice.
And yet, and this is the miracle, by the time that kid is 4 or 5, they are speaking in perfect, complex sentences. They're using rules they have never been explicitly taught. They can create sentences they have literally never heard before. Skinner's copy and paste theory just can't explain that creativity.
So Chomsky's argument is, the math doesn't add up. The input is garbage, but the output is perfect. So there must be a cheat code.
The cheat code is the language acquisition device, or LAD. Chomsky argued that we are born with the rules already inside us. We have a universal grammar hardwired into our brains. We don't learn the rules, we just activate them.
So we come preloaded with the software. That was the dominant theory for a long time. But then computers entered the chat.
Right. Enter the 1980s. The pendulum swings again. A group of researchers, notably Rumelhart and McClelland, introduced connectionism. They wanted to see if a neural network, could learn language without Chomsky's preloaded rules.
This is really the grandfather of the AI we have today.
It is. And the battleground they chose was the English past tense. This is great because English is so weird. We have the rule. Walk becomes walked. Jump becomes jumped. Easy.
But then you have the rebels. Go becomes went. Run becomes ran.
Exactly. Chomsky would say you have a rule for the regulars and then just a memorized list for the irregulars.
Yeah.
But the connectionists, they built a neural network that didn't have any rules. It just had connections.
How does that work? How do you learn a rule without a rule book?
Okay, imagine a grassy field. The first time the computer hears walk and walked, it walks a path through the grass. The grass gets trampled a little bit. Then it hears talk and talked. It walks that same path again. The path gets clearer. It becomes a highway.
You added highway.
That's it. It's just following the path of least resistance. But here is the cool part. What happens when it encounters go? The computer tries to take the highway. It predicts good.
Which is exactly what kids do. My nephew said, I go to the park for months.
That's the key. The computer made the same mistake a human child makes. But then you correct it. You say went. The computer realizes, oops, wrong path. It has to beat down a new tiny path just for go. It learns the exceptions not by a rule, but by the sheer weight of associations.
So the mind people are fighting this war. Is it nature? Is it nurture? Is it rules? Is it connections? Meanwhile, what's happening across town? What are the brain guys doing while the psychologists are arguing about grass paths?
Well, the brain guys, the hardware team, were struggling to even find the motherboard. I mean, if you go back far enough, they were wildly off base.
I love this detail from the source. Aristotle, who was a genius in so many ways, was dead wrong about the brain.
Oh, completely. He thought the heart was the center of intelligence. He looked at the brain, this cold, wet, gray lump, and decided it was a radiator. Its only job was to cool down the blood.
The most complex object in the known universe.
Yeah.
And he thought it was an AC unit.
It took a long time to shake that off. It wasn't until the 19th century that we really started to map the territory. And this brings us to a controversial figure, Franz Joseph Gall.
The name sounds familiar. Was he a surgeon?
A neuroanatomist, but he's famous for starting phrenology. You've probably seen those old ceramic busts with the little map drawn on the skull.
Oh, right. The carnival thing, where they feel the bumps on your head and tell you if you're going to be a thief or a poet.
That's the one. Now, phrenology itself was total pseudoscience. You cannot read personality from skull bumps.
Well, Gall had a radical idea that was actually correct. He argued that the brain wasn't just one big mush that did everything. He argued for localization of function. He said, this part does speech, that part does memory.
So he had the right idea that the brain has specialized departments, but he was using a terrible method to find them. Exactly. The real proof came from the unfortunate reality of medical trauma. A man named Paul Broca in 1861 met a patient who could understand everything said to him, but he could only say one word, tan.
Tan.
That's all he could say, tan, tan, tan. When Broca examined his brain after he died, he found a lesion in the left frontal lobe. That area is now called Broca's area. It's the speech production center.
So the hardware for making words was broken, but the hardware for hearing them was fine.
And then, just a few years later, Carl Wernicke found the mirror image. He had patients who could speak fluently, the words flowed out like a river, but they made zero sense. It was just word salad. And they couldn't understand what you were saying to them.
So the comprehension center was broken.
Right. That's in the temporal lobe, Wernicke's area. But Wernicke went a step further. He said, okay, if we have a listening center and a speaking center, they must be connected, right?
Makes sense. If I ask you to repeat a word, you have to hear it in Wernicke's area, send the data to Broca's area, and then say it.
Exactly. He predicted there must be a physical cable connecting them. And he was right. It's a bundle of nerve fibers called the arcuate fasciculus.
And I assume if you cut that cable, bad things happen.
Very specific bad things. It's a condition called conduction aphasia. You can understand fine, you can speak fine, but if I say the word apple, you can't do it. The bridge is out. You can't transfer the input to the output.
That is fascinating. It's like a phone line being cut. So by the mid-20th century, the hardware guys have a map, they know where the stations are, and the software guys have their theories about grammar and rules. But they still aren't talking to each other.
No. Still attending different conferences. The synthesis, the marriage of these two fields, it needed a spark. And according to the lore, that spark happened in the back of a taxicab.
Okay, set the scene for me.
Picture it. New York City, late 1970s, you have George Miller, a titan of psychology, a mind guy, and you have Michael Gazzaniga, a brilliant neuroscientist, a brain guy. They're sharing a cab, probably stuck in gridlock traffic, heading to a dinner or a meeting.
Forced proximity. The best way to solve a problem.
And in that cab, they start venting. They realize that they are both trying to solve the same puzzle, but with half the pieces. They decide right there to join forces, and they coin a new term, cognitive neuroscience.
The mind and the brain, finally holding hands.
Finally. And this ushered in the modern era, because now we aren't just waiting for people to have strokes so we can see what broke. We have technology. We can look inside the healthy, living brain.
We have the alphabet soup of scanners.
Every-
RI, fMRI, PTT, EG.
But here's the catch. Even with the fancy tech, we still have a trade-off. It's like the Heisenberg uncertainty principle of the brain. You can know where something happens, or you can know when it happens, but it's really hard to know both.
Why is that?
Well, take fMRI. That's the one with the beautiful, colorful blobs on the brain pictures. It measures oxygen in the blood. When a part of your brain works hard, blood rushes there. But blood is slow. It takes seconds to get there.
And speech happens in milliseconds. So fMRI is like taking a long exposure photo of a highway.
Exactly. You see that the road is busy, but you can't see the individual cars speeding by. If you want to see the cars, the split-second timing of language, you need EEG. That measures electricity at the scalp. It's instant.
But I'm guessing, since you're measuring it from outside the skull, it's fuzzy.
Very fuzzy spatial resolution.
Yeah.
You know something happened, but you aren't exactly sure where. But EEG gave us one of the funniest experiments in this whole field, the socks experiment.
Oh, I love this one. Walk us through it.
So researchers hooked people up to an EEG and had them listen to sentences. If I say to you, he spread the warm bread with butter, your brain signal stays flat and calm. You predicted butter, you got butter.
Smooth sailing.
But if I say, he spread the warm bread with socks,
Socks.
about 400 milliseconds after you hear the word socks, less than half a second, your brain produces this massive negative voltage spike. It's called the N400.
It's like a mental faceplant.
It is. It's the brain stumbling. It's a neurological WTF. And what's amazing is that the size of the spike depends on how weird the word is. If I said, he spread the bread with jam, maybe slightly unexpected, but plausible, you get a tiny bump. But socks,
Yeah.
massive spike.
So this proves that the mind isn't just passively recording words, it's predicting the future. It's constantly guessing what I'm going to say next.
And when the prediction fails, the hardware crashes. This is where the synthesis gets really exciting, because we're finally seeing how the software, the prediction, shows up in the hardware, the electricity.
There's one last concept in the source that I think is the biggest game changer. It's called embodied cognition.
Hmm.
And honestly, this one kind of blew my mind.
It reverses everything we thought we knew. For decades, the mind people treated the brain like a computer. A computer doesn't care if it's made of silicon or metal, it just processes symbols. It doesn't have a body.
But embodied cognition says you can't have a mind without a body.
Correct. The theory is that our understanding of language is grounded in our physical experience. Here's the evidence. Put someone in an fMRI scanner and have them read the sentence, "He kicked the ball."
Okay.
Obviously, the language parts of their brain light up, but guess what else lights up? The motor cortex. Specifically, the part of the motor cortex that controls the leg.
Wait, so to understand the word kick, my brain has to secretly simulate kicking.
Yes, your brain creates a micro-simulation of the action. You cannot understand kick in a vacuum. You understand it because you have a leg and you know what it feels like to use it.
This has huge implications.
Yeah.
Think about AI. Think about ChatGPT. It creates perfect sentences. It can use the word kick, but it doesn't have a leg. It has never kicked anything.
That is the billion-dollar question. If embodied cognition is right, then AI doesn't actually understand anything. It's just manipulating symbols. It's a map with no territory. It can talk about love or pain or kicking a ball, but without the biological wetware to feel those things, is it just faking it?
It's the ultimate Chinese room problem. It looks like language, but there's no one home.
Exactly. And that brings us back to the synthesis. We've come a long way from Plato's floating soul. We've gone through behaviorism, innate grammar, neural networks, and now we are realizing that the mind, the brain, and the body are all one tangled mess.
So, have we solved it? Did the taxi cab conversation fix everything?
Gurnham's conclusion is a bit humbling. He says that despite 200 years of fighting and 50 years of scanning, a genuine and satisfying synthesis remains elusive.
Elusive? It sounds like a polite way of saying we are still confused.
I think it's exciting, though. We have identified the pieces. We know the neurons, we know the grammar, we know the body connects them, but we still don't know the mechanism. We don't know how a firing neuron becomes the feeling of a memory. That gap, the hard problem, is still there.
It makes you wonder if we're limited by the very tool we're studying. We're using language to try to understand language. Maybe that's the bottleneck.
It's like trying to see your own eyes without a mirror. You can't quite do it.
Well, until we figure out how to step outside our own heads, we'll just have to keep spreading our warm bread with socks.
And hoping our N400s don't spike too hard.
Thanks for listening to The Deep Dive. Keep those neurons firing, and we'll see you next time.